Hello, my dear teachers. The topic of my undergraduate research is identification of fabrics based on frictional sounds. When objects move across a fabric, sounds are produced. The sounds are so unique, so we can use them to identify clothes. A great number of necessities are made of fabrics. However, they are sometimes in high demand, but how to be widely reproduced due to the identification of fabrics are so time-consuming and labor-intensive. Traditional ways include burn tests and microscopy. Here we use the frictional sounds to perform the tests instead. Because in this era, audio analysis has become a growing subdomain of deep learning applications, so we can employ spectrograms, heat maps that illustrate frequency compositions as they vary with time. Use this graph so we can perform the tests and know that frictional sounds can also identify clothes. Here's the first figure. It is shown that multiple steps are involved in the collection and pretreatment of samples. In the first step, a system for recording is constructed. The red arrow means the pulling forces and the exerting forces on the scouring pad must be kept constant. When audio file is generated, it will be cut based on the endpoint of the sliding, and it will be put into audio analysis to generate a spectrogram. The spectrogram will further be qualified to generate a numeric table, and multiple numeric tables will be put into quality control in order to eliminate outliers existing in a group of samples derived from the same cloth. Here's the results. Okay, so before we talk about the results, let's look at the procedures here. There are two samples. The two samples are compared to each other based on their time frames. Each time frame has specific frequency compositions. So frequency compositions will be compared to each other using PRT tests, and a p-value is generated. Because there are multiple time frames, so there are multiple p-values here. A row of p-values will be generated. And also, combinations with regard to fabrics or other prospective secondary factors are multiple. So there will be a lot of rows of p-values. We summarize the p-values based on the position of the element. So we take the first element as an example. The p-values more than 0.001 will be calculated into a percentage here. So there will be multiple percentages, and the percentages will then be averaged into a value. This value, we define this value as similarity. Here's the results. We can see that similarities within the same fabrics are generally greater than those in different fabrics. Also, the strength of pulling forces and temperature can affect frequency compositions as well. However, we can see that in the fabrics ID 012L2CL, the similarities are very against our hypothesis here. And the reason behind this phenomenon may be careless operations or sometimes unknown factors, including moistures. And we can see that in figure 3, there is very low correlation between times of friction and similarities. So in conclusion, either scouring pad or fabrics can endure at least 13 times of friction and won't change their textures very much. And we can see that in the prediction system, there will be more than 60% of accuracy here. And the accuracy just means the score are not equal to 0. And the score means numbers of correct clause, correct predictions within the top 10 similarities. So in conclusion, we can use these methods to identify clause. Although frictional sounds cannot be fully reliable with regard to the identification of fabrics, it can already be narrowed down the possible ranges of fabric categories in further steps. There is still room for improvement of accuracy. We can improve the accuracy by improving our recording system, and also we can expand the data for reference, so maybe the accuracy can increase in the future. Thanks for listening.